Hi everyone, I am N.R. Bhuvaneshwari, Associate Professor, Department of Mathematics, SNS College of Technology, Coimbatore. Here I have a case study about Newton's law of cooling based on the application of differential equations. So, what is Newton's law of cooling? Newton's law of cooling states that the rate of change of the temperature of an object is proportional to the difference between its own temperature and the ambient temperature, that is, the temperature of its surrounding. Newton's law makes a statement about the instantaneous rate of change of the temperature. We will see that when we translate this verbal statement into the differential equation, we arrive at the differential equation. The solution to this equation will then be a function that tracks the complete record of the temperature over time. So if we form the differential equation for the above verbal statement, we are getting the equation as like this: Newton's law of cooling. Capital T denotes temperature, small t denotes time. So T of t is equal to T alpha plus T naught minus T alpha of e power minus kt. If you are differentiating this differential equation, we get this dt by dt is equal to minus k of t minus t naught. And this graph represents x-axis is time domain and y-axis represents the temperature in terms of degrees Celsius. Let us see the application of Newton's law using the concept of design thinking. But what is design thinking? Yes, design thinking is a non-linear iterative process which seeks to understand users, challenge assumptions, redefine problems, and create innovative solutions to prototype and test. The method consists of 5 phases: empathize, define, ideate, prototype, and test, and is most useful when you want to tackle problems that are ill defined or unknown. The big pot of soup. As a part of his summer job at the restaurant, Vijay learned to cook the pot of soup late at night, just before closing time, so that there would be a soup to feed customers the next day. He also found out that while refrigeration was essential to preserve the soup overnight, the soup was too hot to be put in directly into the fridge when it was ready, which I discovered that by cooling the pot in a sink full of cold water and stirring occasionally, he could bring the temperature of the soup of 60 degrees Celsius in 10 minutes. How long before closing time should the soup be ready so that Vijay could put it in the fridge and leave on them? Okay, let's have the empathy part for the above problem. Analyzing the situation of Vijay, leaving time of Vijay should also be considered. Could not use the refrigerator to store the boiling soup. Define. To narrow down the situation to a point which is more relevant to the situation of Vijay, by which we can come to the conclusion. Considering the various points if is necessary. Vijay needs to be on time. Soup should be cooled down to the temperature at which it would be safe to place it in the refrigerator, and how long before the closing time Vijay should start to prepare the soup. Ideate. Allow a stream of water to pass through the soup pot. Make a constant stirring so it cools a bit or faster. To switch on AC and fan if available. To open up the window for perfect air ventilation. Prototype. We are having an example. The soup had just boiled at 100 degrees Celsius and fridge was not powerful to accommodate a big pot of soup if it was any warmer than 20 degrees Celsius. Vijay discovered that by cooling the pot in a sink of cold water kept running so that its temperature was roughly constant at 5 degrees Celsius. He could bring the temperature of the soup to 60 degrees Celsius in 10 minutes. How long before closing time should be soup be ready so that Vijay could put it in the fridge and leave on time? We are having the differential equation solution based on this example. Let us determine how long it takes for soup to be cool enough to put it in the refrigerator. We need to wait until. So based on the above example, we form the differential equation in terms of the form 20 is equal to 5 plus 95 exponential to the power minus 0.0540. This equation can be solved for in much the same way as before, subtracting 5 on each side and dividing by 95 for our simplification, and we are getting in terms of logarithmic. Then logarithmic of 6.33 is equal to 0.0540. After the simplification, t becomes 34.18. Thus, it will take a little over half an hour for Vijay's soup to cool off enough to put it into the refrigerator.